We are now on the third and final law of thermodynamics. The entropy of a perfect crystal at 0 Kelvin is 0. Okay? That word perfect in there should let you know that this is unobtainable. This is just for reference. So if we had a perfect crystal at 0 Kelvin, there would be no vibrations, so the entropy would be 0. But as you increase temperature, vibrations will increase, the particles will move, entropy will increase. We increase it enough and we're no longer even a crystal. We would have changed our state of matter. So here is our equation. Delta S of the reaction, and remember that 0 means standard conditions, which means a reference chart in the appendix. It has H values, S values, and G values, all at 0 and all probably the delta in between them. Okay, so moles times the entropy for the products, sum them all up, minus the reactants. This should look familiar because we did this back in our thermochemistry chapter using the delta H values. Ooh, too far. And too far again. You'd think I'd have scrolling down by now. Okay, so here we go. We need to predict our delta S values. So we have 3 moles of gas, and we go to 2 moles of gas. So we're predicting a negative delta S. Okay. Now, to do the calculations, we need the appendix in the back of the book. So I'm going to pause and go find the book. All right, so remember Appendix 4 in the back of the book. We used this when we just needed the delta H values. You got a handout. It was blue, and you remember those lists of data? It was tiny, and you had to be very careful to read the correct line. Okay? It's organized by element. H2S was under the sulfur. Obviously, so were SO2 and the S solid that was rhombic. Important that you pick the one that was rhombic, not monoclinic. H2O, make sure you grab the one that is gas and not accidentally the liquid. Now, all of these S values are in joules per Kelvin mole. So we have, come back up here and look at it. Our delta S of the reaction is the sum of products minus reactants. So our products, we've got 3 times 32 plus 2 times 189. I'm leaving the units off since they're all the same. And it's products minus reactants. So for our reactants, we have 2 times the 206 and the 248. There's no coefficient on that. So I've got 3 times 32 plus 2 times 189. And that's giving me 474. So I'm going to write that down. Now I'm going to simplify the other part. 2 times 206 plus 248. And I get 660. So now 474 minus 660 gives us negative 186. And now I'm going to put my units on it. And that is my delta S for the reaction. And it is indeed a negative number. As just comparing the moles, let us predict that we would have a negative number. Okay. More complex molecules have a higher delta S because the more complex the more possible arrangements. Not of the atoms, but more like just the physical space of the molecule. Figure like a bigger molecule can twist more.